Good morning, everyone. So, the next question that we'll see today is question number 13. Here it says, prove by the principle of mathematical induction that number one is this n in bracket n plus 1 into in bracket n plus 2 is a multiple of 6. So, we have to show that for every natural number, okay, this expression will be a multiple of 6. So, solution, you'll write let Pn is multiple of 6. This is the first thing that you will do. Then you will check, or you have to prove for n equal to 1 that this expression will be multiple of 6. So, for n equal to 1, the given expression is, so in place of n I'll put 1. So, I'll get 1, 1 plus 1, 1 plus 2. So, 2 into 3, that is 6. Okay. So, for n equal to 1, the given expression, this is multiple of 6. Yes, 6 is multiple of 6. Therefore, P1 is true. P1 is true. Now, next is to assume that Pk is true. So, now let Pk be true. So, when I say Pk is true, that means here if I replace n by k, then whatever expression you obtain will be multiple of 6. So Pk, that will be k, k plus 1, k plus 2 will be, or you say is multiple of 6. So if this expression is multiple of 6, that means this expression can be written 6 times some natural number. Yes. So this implies k, k plus 1, k plus 2 is equal to 6 times m. Okay. Where m belongs to natural number. Okay. For some natural number. Like here you can see that you got 6. That means 6 into 1, 6. Yes. So we got this. You have to give this as equation 1. Now we have to show that the expression will be true for k plus 1 also. Okay. So you write now. So you have this expression. Okay. So what you have to do? You have to copy this, but only thing is that wherever is k, that should be replaced by k plus 1. So now k plus 1, that means for this k I wrote k plus 1, and for this bracket 1 I will write k plus 1 plus 1, and here k plus 1 plus 2. Okay. So you wrote this. Now what you have to do is you have to simplify this. Okay. And you have to simplify such a way that one term should be this also. Okay. On the right hand side you should get one term as this, so that you can make use of this. Okay. So now what we'll do is k plus 1, see in this bracket we can write k plus 2, and for this bracket we can write k plus 3. Okay. Now I want to use this k plus 1 into k plus 2 is equal to 6m. Okay. I want to use this equation 1. So what I can do is here you can see this is k plus 1 into k plus 2. So here also we have k plus 1, k plus 2. The only thing over here, into k is missing. Yes, if there had been k times k plus 1 into k plus 2, then in place of that we could have easily written 6m. Yes, so what we'll do is we will multiply this whole thing with this. Okay, so this whole thing will multiply with k1, so you'll get k times k plus 1 and k plus 2, done. Then plus sign, and then this whole thing will multiply with this 3, so you get 3 times so now you can see this is k into k plus 1 into k plus 2. So you know that from equation 1 this is equal to 6m. Yes, so you can write 6m plus 3 times this, and you can write from 1. Okay, so you can see that altogether you have got two terms, one is 6m and one is this 3 times k plus 1 into k plus 2. Now if you could show that this term is also multiple of 6, then your work is done. Okay, so here this is a constant number 3, and here we have k plus 1, k plus 2. Okay, so here what do you observe is this is, these two are conjugate numbers. Okay, like k plus 1 and this k plus 2 is nothing but k plus 1 plus 1. So can you see this is conjugate? Okay, not conjugate, sorry, consecutive integers. Okay, these two are consecutive positive integers, like because k is natural number, so positive. So you know that if you take product of two consecutive positive numbers, okay, positive integers, then product will be always even. Like if you say if you take 2 into 3 you will get 6, if you take 3 into 4 you will get 12, if you take 4 into 5 you will get 20. So can you see you are taking product of consecutive positive integers, and in product you are getting even, that is 2 into 3, this is 2 into 6, this is 2 into 10. Yes, so here also k plus 1 into k plus 2, so here we are taking product of two consecutive positive integers. Yes, so obviously this will be 2 times something. Okay, this product will come even. Okay, so we can write 6m plus 3 times. Okay, and for k plus 1 into k plus 1 plus this, we can, since we are taking product of consecutive integers, positive consecutive integers, so I can write 2 times, let's say p. Okay, and I can write where 2p is equal to k plus 1, k plus 2. Okay, because these two are two positive consecutive, so product will be even, that means 2 times something. Okay, where 2p is this and p belongs to natural number. Okay, so you get 6m plus 6p. Okay, so 6 is common, you got m plus p. So here what do you observe, that you observe that k plus 1 into k plus 1 plus 1 plus k plus 1 plus 2, you are getting multiple of 6. Okay, so this implies the statement pk plus 1 is multiple of 6. Okay, is multiple of 6, Therefore pk plus 1 is true whenever pk is true. Hence, by principle of mathematical induction, Pn is true for all n belonging to natural number. Okay, so this is done. Okay, this is your homework. Here is saying, using the principle of mathematical induction, prove that n square plus n is even for all n belongs to natural number. That means you have to show that this is multiple of 2. Okay, so you have to do same as the one we have done just now. Okay, now let's see the next question. Here he says, prove that n plus 1 into n plus 5 is a multiple of 3 for all natural number. Okay, so solution: let Pn n plus 1, this is multiple of 3. For n equal to 1, the given expression is 1, 1 plus 1, 1 plus 5, so 2 into 6, that is 12, 3 into 4, okay, is multiple of 3, okay. Therefore P1 is true. Done. Now we have to assume that pk is true. So now let pk be true. Then pk, so for pk what we have to do, we have to copy this expression. Only we have to do is change the n, replace n by k, so you get k plus 1, k plus 5 is multiple of 3, okay, and since it is multiple of 3, this implies k plus 1, k plus 5 will be equal to 3 times some positive integer, okay, where m belongs to natural number, okay. Give this as equation 1. Now we have to show that this is true for k plus 1, okay. So for that, right now, so you have to copy this expression. The only thing is, we'll in place of k we'll write k plus 1. So now k plus 1, k plus 1 plus 1 and k plus 1 plus 5, okay. Now we will simplify and we'll try to make use of this equation 1, okay. So we get k plus 1, here k plus 2 and k plus 6. We want to get this actually k plus 1, k plus 5, so that I can put 3m, okay. So here I have k plus 1, k plus 5 is not there, but k plus 5 can be obtained from here, k plus 6. Okay, so I can write like this: k plus 1, k plus 5 plus 1, and here k plus 2. Now next what I can do is I can multiply this k plus 1, okay, with this and then with 1. So I will get k plus 1 into k plus 5 and then plus for this one, and I'll get k plus 1 into 1, so simply k plus 1. Okay, so I got this, and outside here k plus 2. So now you can see that here we have k times k plus 1 into k plus 5, so, but here we have only k plus 1, k plus 5. If there had been k, okay, with this, then we could have easily put 3m. So we need k over here. So if we multiply this, okay, with k, then I can get, yes, so we have to multiply these terms in bracket, okay, with this one. So we get k times k plus 1, k plus 5, because this is multiplying with k, okay, and then plus 2 times k plus 1, k plus 5, and then this k plus 1 will multiply with this one. So plus k plus 1, k plus 2. So now in place of this k plus 1 into k plus 5, I can put 3m, okay. So I'll write 3m, and here I can see that for these two, k plus 1 is common, so I can take that out, and then I'm left with 2 times k plus 5 and k plus 2. Okay, so open the bracket now. So you get 3m, k plus 1 here, and here you are getting this 2k, and this 1k will become 3k, and this 10 and this 2 will become 12. Okay, we got this. Now in this bracket you can see 3 is common, so 3 will come out. So we get 3 times k plus 1, and here in bracket k plus 4. Okay, and now in these two terms 3 is common, so 3 comes out. So m plus so clearly you can see that k plus 1 plus 1 and k plus 1 plus 5 is multiple of 3. Okay, so this implies that the statement pk plus 1 is true whenever pk is true. Okay, pk plus 1 is true whenever pk is true. Okay, clearly you can see this is multiple of 3. Okay, So therefore pk plus 1 is true whenever pk is true. Hence by PMI Pn is true for all n belonging to natural number. Okay, so this question is done. Now let's see the next one. So here we have to prove that this expression is divisible by 2 for all n belonging to natural number. Okay, so let Pn be this 3 to the power 2n minus 1 plus 3 to the power n plus 4, okay, is divisible by 2. When I say it's divisible by 2 means this is multiple of 2 actually. Okay, now for n equal to 1, the given expression is 3 to the power 2 into 1 minus 1 plus 3 to the power 1 plus 4 is equal to 3 to the power 1 plus 3 to the power 1 plus this. So here 3 plus 3 6 plus 4 10, 2 into 5. So clearly you can see that this is divisible by 2. Okay, is divisible by 2. Simply divisible by 2, because here we have already used is. Expression is this divisible by 2. Okay, done. Now therefore P1 is true. Next we have to assume that Pk is true. Okay, so now let Pk be true. So Pk is true, that means Pk 3 to the power 2k minus 1 plus 3 to the power k plus 4 is divisible by 2. Okay, and if it is divisible by 2 means this implies that 3 to the power 2k minus 1 plus 3 to the power k plus 4 is equal to 2 times some positive integer. Okay, so where m belongs to natural number, give this as equation 1. Okay, okay, now we have to show that this pk plus 1 is also true. Okay, so for that now you have to copy the same expression. Okay, the only thing is wherever is k, replace by k plus 1. So now 3 to the power 2 times k plus 1 minus 1 plus 3 to the power k plus 1 plus 4 is equal to, now we have to simplify this, and sometimes somewhere like we have to manipulate also so that we can get exactly this. Okay, so that we can replace that by 2m. So see over here, we can write 3 to the power 2k plus 2 minus 1 3 to the power k into 3 to the power 1 plus 4, 3 to the power 2k minus 1 3 to the power 2 3 to the power k into 3 plus 4. Now you can see we haven't got this till now, okay, but we will try to get this one, okay, even if we have to manipulate over here. So we should manipulate and get this expression somewhere here, okay, so that we can straight write 2m, okay. So see over here, this is 3 square means 9, so I can write 9 times 3 to the power 2k minus 1, and here this is 3. So instead of writing, okay, first let me write like this. Done. I want only this much, 3 to the power k minus 1 plus 3 to the power k plus 4. I need this, okay. So here we can see that before this 3 to the power 2k minus 1 we have got n in multiplication, yes, sorry, 9 in multiplication. So we have to try to remove this, okay, means we have to try to make this as common, okay, and take it out. So what I will do is I will write 9 times 3 to the power 2k minus 1, and here it is 3. If this had been 9, no, then we could have easily taken 9 as common from these two terms. So what I will do, I will write 9 times 3 to the power k, and then I will subtract this 6 into 3 to the power k, okay. So that means what I have done is this same term I have expressed as these two, okay. Now next I need 4 also, plus 4, okay. So I can write like this, 9 into 4 minus 9 into 4. So here I'm adding and subtracting, okay, and this 4 is same. Now in the next step what I can do is I can write this, this and this together, okay. So I will get 9 times 3 to the power 2k minus 1 plus 9 times 3 to the power k plus 9 times 4, and here we will get minus 6 into 3 to the power k, and here you will get 36 minus 36 minus 36 plus 4, so you will get minus 32, okay. And here from these three terms, okay, 9 is common, so 9 comes out. So you are left with 3 to the power 2k minus 1 plus 3 to the power k plus 4. And here 6, okay, 1 second. Here this is 6, here this is 32. So you can see that 2 is common, yes. So I can write like this, 2, here 3 into 3 to the power k plus 16, okay. And here for this much I can write 2m, yes. From 1 we can write that as 2m. So I can write 9 into this 2m, and here minus 2 times this one, 3 into 3 to the power k, so this can be written as 3 to the power k plus 1 plus 16. So 2 is common, so 2 comes out, so you are left with 9m minus 3 to the power k plus 1 minus 16. So you can see that you got this as multiple of 2. That means this whole expression is divisible by 2, okay. So now here I can write, this implies 3 to the power 2 times k plus 1 minus 1 plus 3 to the power k plus 1 plus 4, okay. and this implies this is the statement pk plus 1 3 to power 2 times k plus 1 minus 3 to power k plus 1 plus 4 is equal to 2 times 9m 3 to power k plus 1 minus 16. Okay, so you can write therefore pk plus 1 is true whenever pk is true. Okay, hence by principle of mathematical induction Pn is true for all n belonging to natural number. This is done. Okay, now see the next question. So here it says prove that 3 to the power 2n minus 1 is divisible by 8. So solution, let Pn 3 to the power 2n minus 1 is divisible by 8, is divisible by 8. Okay, now for n equal to 1, okay, 3 to the power 2 into 1 minus 1 will get 9 minus 1 equal to 8 is divisible by 8. Yes, therefore P1 is true. Clear? Now next thing is to assume pk is true and show that pk plus 1 is true. Now let pk be true. That is pk 3 to the power 2k minus 1 is divisible by 8, is divisible by 8. And once I say it's divisible by 8, that means this whole expression is multiple of 8. So this implies 3 to the power 2k minus 1 is equal to 8 times m, where m is some natural number. Okay, give this as equation 1. Now we have to show that pk plus 1 is also true. So now you have to copy this only, but the thing is wherever is k, replace that by k plus 1. So you get 3 to the power 2k plus 1, okay, minus 1 is equal to, now you have to try to get this term, okay, on the right, so that you can replace that by 8m. Okay, so here this becomes 3 to the power 2k plus 2 minus this. Next this will become 3 to the power 2k into 3 square minus 1, and 3 square means 9. Okay, so here you get, now see over here, I want to get 3 to the power 2k minus 1, okay, but here I have 3 to power 9 into 3 to the power 2k. Okay, so what I can do is, and I need minus 1, okay, so here I can do this, 9 into 3 to the power 2k minus 9 plus 9 minus 1 of this. Okay, so I'm adding and subtracting 9. Clear? And then 9 will be taken common from the first two terms, so we get this 3 to the power 2k minus 1, and here 9 minus 1 will be 8, and this 3 to the power 2k minus 1 will be 8m, so you get 8m. If you want to write, you can write from 1. Okay. Now you can see that 8 is common, so 8 comes out, so you get 9m plus 1. Clearly this is multiple of 8, that means divisible by 8. So you got 3 to the power 2k plus 1 minus 1 is equal to this. This implies pk plus 1, 3 to the power 2k plus 1 minus 1 is equal to 8 times 9m plus 1. Done. So therefore pk plus 1 is true whenever pk is true. Done. Hence, by principle of mathematical induction, Pn is true for all natural number belongs to, for all n belonging to natural number. Okay. So this is done, and this is all for today.